Welcome to example number 6 in chapter 9 on rotational dynamics. So we have a picture shown over here on the right with 4 tiny spheres fastened at the corners of a frame, shown in blue here, with negligible mass. We shall assume the sphere's radii are small compared to the dimensions of the frame. So the system is going to be rotating along the XY plane. Now this is a little bit hard to sort of visualize, so I decided to make a little program in GlowScript to visualize this. We'll do this in class as well, I hope. So here I've constructed this in GlowScript, and I've got 4 spheres, and I've also labeled my axes X, Y, and there's actually a Z axis coming out of here. So you just press click and play here, and you can see it's rotating, but it's rotating in the XY plane. So if I were to kind of just shift my view, you hopefully can see that it's rotating like that. That's a little bit hard to see in the notes that we have done, but I'm basically looking at a system that is rotating in that XY plane. And that's really important because if we were calculating a rotational inertia of a system that was rotating, say, along the YZ plane, then it would be a different amount. Okay, back to the problem in our notes here. We need to find the moment of inertia of the system. So if you recall, the moment of inertia of a system is given by sum of mi r sub I squared. So we're adding all of them. So essentially this means we're going to take the first mass, we'll label this m1 times r1 squared. Then we have the second mass, we'll call that m2 times r2 squared, plus this mass, which is m3 times r3 squared, and we have m4 and r sub 4 squared. So we can start substituting our values in. M1 is 3 kilograms, but we've got to put the distance squared in there. So the distance r is the distance from the center of the axis of rotation to the distance to the point where all these masses are at. And if you look at this problem, it involves a lot of symmetry, and all of these distances r are all the same. So I'm redrawing this triangle over here, and we can see that this side is half of 4, which is 2, and then this side here is half of 6, which is 3. So if we use Pythagorean theorem, r squared is equal to 2 squared plus 3 squared, we'll see that r squared is equal to 13. So we know that this is root 13, or just simply, if you do that squared, it's just going to be 13. And then we just continue with the other masses. We have the 2 kilogram mass, and then that's at the same distance. And then we have the 2 kilogram mass, the other one, that's also root 13. And lastly, you have the 4 kilogram mass, and that's at root 13. I'm forgetting to put units of meters in here, but oh well. So now I'll pull up my calculator and calculate all that. And that adds up to a rotational inertia of 143 kilograms times meter squared. Okay, now let's go on to part B. We're trying to find the rotational kinetic energy, which is given by 1/2 I omega squared. Now you've already calculated I up there, which is 143. So all you need to know is what the angular velocity is, which is 6 rads per second. So we just substitute in here 143 kilograms times meter squared times 6 rads per second quantity squared. And that gets you an answer of 2,574 joules. And that's it for this example.